This is Uncovering Chemistry by Joy Varghese. Last time in video 16, 15, 16, 14, 13, all whatever videos we saw, in that we have discussed about the basic stereochemical principles, right? In which we discuss optical activity, that was discussed in video 15, chirality in video 15, respiration in video 16. Today we will be discussing little bit about retention, that is retention of configuration, which we have already discussed in video 14, SN1 mechanism, and inversion, that is inversion of configuration, discussed in video 13, SN2 mechanism. Now when we talk about this, you remember this kagdo the, what we say, no, in rainy season, umbrella gets inside out. So this all we have already discussed, but from your textbook we'll little bit will discuss a part of it. Okay, so see in your textbook what is written here. I think you can see the topic. It is given on page 308. What is written here? Retention. The retention of configuration is the preservation of a spatial means according to availability of space, arrangement of bond to an asymmetric center. Asymmetric center means carbon, what we say, in which all the groups must be different during a chemical reaction or transformation, what is given here, right? Now when we talk about this part, you can easily see here. In this case, if you see all the groups, this is your asymmetric center carbon. Asymmetric center carbon. This all the groups, if you see, no, are different, what we say, right? That's why it is asymmetric. So here this is the leaving group, this is the attacking group, right? So what happens when the leaving group is removed from here, an attacking group gets substituted here, but you will see there is no change in the configuration. Means everywhere you will see the substituents are same before reacting and after reacting. That's why it is called retention of configuration, right? What it is called? Retention of configuration, right? But if you see here, there is a change in sign, means this is negative, means levorotatory compound, and this is positive, that is dextrorotatory compound, right? So here you can see it is important to note that configuration at the symmetric center in the reactant and the product is same. What is the word? Configuration of the reactant and product is same, but the sign of the optical rotation has changed in the product, right? Now this you have to remember. So this is what we call it as retention of configuration, right? Now same way when we talk about the next part, what we say here, the next part is inversion of configuration. Now this retention we discussed, retention we finished, respiration also we finished. Now inversion. Now in this case all these three things are explained. See now how. Here if you see, in this case what is there, all these groups are, this is your asymmetric center in all these three, what we say, right? This is your reactant. What is the word? This is your reactant, and these two are the product. These two are the product, right? Now in this case if you see, you can see all the groups are on which side? Left side. Here also on the same side, so we can say this is what? Retention of configuration, right? This is that product A, what we call. Now here the Y has attacked from this side only, we will see here, right? Now in this case, now again this is the reactant. In this case if you see, this group is on right side and this all group is on which side? Left side. So we can call this as a inversion has occurred. What has occurred? Inversion, because all the groups went on the either side, means the configuration has changed. So this is inversion. Now this is your product B. Now this is left side, what we say the rotation, what we got here. A if I take 50% here, and here B if I take 50%, so 50% of dextro levorotatory and dextrorotatory, what we say. So this A plus B is nothing but what we call it as a racemic mixture. What it is called? Racemic mixture, right? So this part understood, everyone? So why it is called racemic mixture? Because 50% levorotatory and 50% dextrorotatory, right? So this one was example of inversion from reactant. This one example of retention. So I think this part is clear, right? So here you can see what is written at the end of your textbook. If A is the only compound obtained, A means this one, the process is called what? Retention. Have we written here retention of configuration? Note that the configuration has been retained. Here it is being changed, so you better it is wrong, so that's why you change this in your textbook in A. If B is the only, B means this part, and you can see it is on which side, either side, is the only compound obtained, the process is called inversion of configuration, and configuration has been inverted, right? This is what we have seen. Now if I mix this A and B, what we'll get? Racemic mixture. So that is also given in your textbook, you can see here, right? What is written here? If 50-50 ratio mixture of A and B is obtained, then the process is called racemization, and the product is optically inactive. That we have already discussed in the further videos. And as one isomer will rotate the plane polarized light in the direction opposite to another, because one will be dextrorotatory and another will be levorotatory. Okay. Now SN1 and SN2 we have already discussed. SN1 shows retention of configuration and SN2 shows inversion of configuration. So here if you see, this is an example of SN2. You can see this one is an example of SN2, and here what stereochemistry? Inversion of configuration will take place, right? Configuration. So here you can see SN2 reaction, optically active halides accompanied by inversion of configuration. Same way this one is an example. This one is an example of SN1 mechanism, and we know it is showing retention of configuration, right? So when we talk about in this retention of configuration, you can see first step is which step? Slow step, that is step 1, and slow step is a rate determining step. Here you can see this carbon is sp3 hybridized, right? Because 8 electrons are there, right? Because it is combined at 4 places. Now this same thing if you see here, first we know the first step, that is formation of C+ ion carbocation, right? So in this case, first step, here carbon is sp3 and here the carbon is sp2 hybridized, right? And that is given in your book, so you can go through it, right? So it will be easier for you, right? Other all things are common, what we say. And the first one we discuss, the mixing here, what we say, from here, this is a reactant, what we call, what is this? And reactant, if you see here, what will happen? This all CH3, this all group are on which side? Either side, what we say. Either means this side. So here minus, that is butane 2-ol, what is written here. You can see the OH attack from which side? From this side. And in this case, OH has attack from the either side. So if you see here, you can see this all groups are on the same side. So this is butane 2-ol, right? So if I mix this A, suppose structure A, and this compound B, if I mix A plus B, what you will get? Racemic mixture you will get, right? So this was the topic what I wanted to discuss from your textbook. Now we will be discussing about this elimination reaction. Which reaction? Elimination reaction, that is page number 309. Now in elimination, I think we have already discussed in your 11th standard class. What is elimination reaction? The reaction you can see here. Alpha carbon is the one which bears the halogen. Beta carbon, that is next to alpha carbon, is called beta carbon. So this comes in the chemical properties, page 309. It is given in your textbook, elimination reaction. Now if I take alcoholic KOH and heat the mixture, what will happen in this case? Halogen is removed from alpha position and hydrogen is removed from beta position. So what will happen in this case? Between these two, alpha and beta carbon, you will see there is a formation of double bond, right? So in this case, you can see halogen is removed from alpha carbon, that is the Br, what we say here. You can see here, this one is removed, and hydrogen is removed from beta carbon. That is the reason why we call it as beta elimination reaction. Why? Because hydrogen is removed from the beta carbon. That's why we call it as beta elimination. Now what is formed between these two? The double bond is formed between alpha and beta carbon. Now this one was a simple example. One another example is given in your textbook. We will go through it. You can see here. Now you can see in this book, you can see this is the reactant, what we say. Now if the OH, you can see this is OH is nothing but what we use the last time what we discussed. This is alcoholic KOH, right? So if you remove, this is your alpha carbon and this is your beta and this is also beta, right? So if you remove a hydrogen from here and from alpha carbon Br, so you will get this product. This is your alpha and beta, what we say, right? So because this is, we can see here, This is from here, what is removed from alpha? Br is removed, and from H you can see here H2 is there. So from here hydrogen is removed. So if it is removed from these two position, obviously you can see this is the product what you get, that is pen2 in. How much percent it is? 18%, right? And same way if you see in this case, hydrogen is removed from this position and Br is removed from this position, means this two you will see here, there is a formation of which bond? A double bond is there, right? So you can see here, what is the word, what we say here? Pen1 in is the product what we get, and it is how much percent? 19%, right? Now this one here we are going to study from this one new rule, Z-safe rule what we call, that is what? If there is a possibility of formation of more than one alkene due to the availability of more than one beta hydrogen atom, what we say. So that what we have discussed. Here also beta hydrogen is there, and here also beta hydrogen is there, right? So usually one alkene is formed as a major product. Now which will be the major product? That was explained by whom? The Alexander Sedzev, what we call, right? Here this form a part of a pattern first observed by Russian chemist Alexander Sedzev, also pronounced as Sedzev. You have to pronounce like, not Zedsev, okay? So who in this formulated a rule which has been summarized as in dehydrohalogenation. Why it is called dehydrohalogenation? Because hydrogen and halogen is removed. That's why dehydrohalogenation. The preferred product is that alkene which has the greater number. What is the word? The word is here preferred. Preferred means here major product. Which product? Major is the one which has greater number of alkyl group attached to the doubly bonded carbon atom. So here if you see here, you can see in this case, this is one alkyl group which is that is methyl group, and here if you see, this is ethyl group, right? So methyl, and this is methyl, and this is ethyl. So there are two alkyl groups which is present in this. That's why it is 81%. Now if you see this product, you can see here, there is no this double bond carbon, only one side. There is only one group. Which is the group? Propyl is the group. Only one alkyl group. What is the word? One alkyl group in this. That's why it is less. And here percentage is more, means it's a major product. Why? Because there are, in this case, there are two alkyl group. Which are that two alkyl group? Ethyl and methyl. So I think this understood everyone. What is Sedzev rule? Which one will be the major product? The one which contain more number of alkyl group next to the double bond carbon is the major product, and one which contain less number of alkyl group next to the double bond carbon is called the minor product. Okay, so this part is clear. So next time we will discuss about the third chemical property, that is reaction with metals. Okay, thank you.